Greetings. In this video, we observe the design and simulation of a low-pass active filter. It is built from operational amplifiers and is based on the Chebyshev filter profile. Our musical accompaniment is by Johann Sebastian, the 6th Brandenburg. This is the book we use to find the equations and the design technique we'll use for this filter. It's by Schaumann from Portland State. Here's a page from the book. You can create the transfer function squared, over 1 plus epsilon squared. This is a parameter we'll calculate. C sub n is the Chebyshev polynomial, named after Newton Chebyshev, Russian mathematician. Here is the frequency profile of Chebyshev low-pass filter. It's at a high magnitude near 1, and it drops off when we get past the pass band of the filter. Now, these ripples are exaggerated in magnitude. They're not really very far down below 1 magnitude here. Here are my initial calculations on paper. They didn't show up very well, but let's look at the cascade that we're going to design here. It's a cascade of 3 different active sections based on operational amplifiers. Vn is on the left, Vout over here on the right. The first element on the left is based on an operational amplifier. It's a first order section, an inverter. Our second cascade element is a biquad, a second order section. It's based on a single operational amplifier, and this is called the Sallen-Key conformation. We'll calculate the magnitudes of these resistors, and we'll set the capacitors to 0.1 microfarad. And this resistor right here, we'll set it at 10 kilo ohms. This is the third element in the cascade. Here's what the Sallen-Key biquad looks like. C1 and C2 will set, and G2 and A times G1, or R1 over A. Here we have 1 minus A times G1, or R1 over 1 minus A. We have a relationship between RA and RB that we'll calculate based on this parameter B that we will derive. We'll start off with the problem statement. Design low-pass filter with Chebyshev response, alpha max is 0.25 decibels, alpha min equals 18 decibels. And our pass band here at low frequencies, we don't want very much attenuation. We're trying to pass the signal. And in the stop band, we're trying to stop any of the magnitude from getting through. Pass band edge is 1000 radian per second, omega p. Omega s, the stop band edge at 1400 radian per second. And we'll scale the magnitude so element values in the circuit are in a practical range. Epsilon is the parameter we just talked about. 10 to the alpha max over 10 minus 1 to the 1/2. We calculate epsilon. And the order of the filter, logarithm of 4 times 10 to the alpha min minus 1 over 10 to alpha max minus 1 to 1/2, logarithm of omega p plus omega p squared minus 1 to 1/2. We get 4.8 and round that up to 5, of course. Here's a parameter A, and I'm sorry this didn't show up very well. It's 1 over n arcsine, 1 over epsilon. We calculate that as a constant. Here on the right is a sketch that didn't show up very well, but it shows the pole locations. They're on the left half plane. Here's a sigma axis, or the real axis, the imaginary j omega axis. Sin A, hyperbolic sine of A, cos A calculated. So here's an equation for our Chebyshev poles from the book. Sigma k was negative sin A, sine 2k minus 1 over 2n pi. Omega k, the imaginary part of the pole, cos A, cosine 2k minus 1 over 2n times pi. We calculate sigma 1 and omega 1 here. And we have our natural frequency for one of our biquad sections. This is the first one on the right. We have that number. We calculate the quality factor, Q1, 3.875. This is the largest magnitude quality factor that we have, so it will be last in the cascade. The second pair of poles in the denominator we have here, and we have our natural frequency and quality factor for the second biquad section. For k equal 3, this is the first order section. The pole is a real number with no imaginary part. It's on the real axis. And we have omega 03, we found that. Quality factor for this odd pole is always going to be equal to 1/2. Unfortunately, the expression of the Chebyshev polynomial did not come through very well. We make the variable transformation from omega to s over j. We find the coefficient of s to the 5th is 2 to the n minus 1, or 16. So what will be the magnitude in our numerator? Well, it's going to be 1 over 16 epsilon, because we are normalizing to get s to the 5th in the numerator. Here we have a numerical value for our transfer function, t sub 5 of s. 5 is the order of the filter. We have 0.2568, capital K in the numerator. Here we have the first order section. We have a second order section here. Oh, sorry about that. And we have our, get our image back on here. And we have a second order section. So what is the gain at 0 decibel? We'll plug in for s equals 0. We get 1.0 as required because it's a low pass filter. So here we are, our Sallen-Key biquad conformation. And T5 is equal to T1, T2, T3. We split the transfer function up into 3 factors with a k in the numerator and a polynomial in each denominator. And k1 times k2 times k3 is our cap k. And each one of these without the k, if the k is replaced by 1, is going to be called our lowercase t functions, t1, t2, t3. And we'll determine the maximum magnitude of each one of those 3 functions. It's part of the algebra we have to do. So m1, the maximum of t1, is going to be with s equal to 0, 2.28. t2 is going to be equal to m2 is going to be equal to the maximum of t2 times max of t1. Calculate that here. Total gain is 0.0 in our pass band. Using algebra and just equations in the book, we can calculate these m coefficients and get our k coefficients for our transfer function. And here we have it numerically in 3 different fractions. This is kind of interesting because our circuit elements, the resistors we calculate, and the capacitor magnitudes we use, they will be determined by the numbers in each one of these 3 components of the transfer section. That's kind of interesting. You calculate these and put in for resistance and find that the filter actually works. Alright, we go through, we calculate the resistances for the first order section, 1 over omega 0 c, right up here. Here we have our R1 and R2 in the first order section. For the second order biquad, Sallen-Key second order sections, set C equal to 0.1 microfarad. And here is a T of S. We're breaking our numerator into these factors, A, B, omega 0 squared. And there's reasons why, because we can derive some of our other values from that. Q, the quality factor, is equal to 1 over 3 minus B. And I'm sorry this didn't show up very well. We calculate R1 and R2, 13.66 kilo ohms. And B is 3 minus the quality factor 2 to the minus 1. And A is unfortunate we used A twice in our derivations here. We have our A factor and our B factors. R1 over A, we calculate that. R1 over 1 minus A. For RA and RB, RB is equal to B minus 1 RA. So we have that for both of our second order sections. Third biquad is calculated here. So exactly how are we going to determine these values? We're going to use a Matlab program. It'll calculate the value of all those resistors. We simply input A max and A min, alpha max, alpha min for the maximum attenuation in the pass band, minimum attenuation in the stop band, the pass band edge and the stop band edge in radian frequencies. We normalize them here. Our standard capacitance, we calculate our coefficient, our variables epsilon. We find the order of the filter here. Now this program goes through and logically determines different ways to respond whether n is even or odd to calculate the poles. And here we are calculating the poles of the Chebyshev transfer function. This is what is called an all-pole filter. there are no zeros in the numerator, and if there were, it would be no problem. Calculate our coefficients m and k to get the factors for the transfer function. And here we determine the resistors that we will plug in at different points in the circuit. We plot right here. So let's run this program, see how it goes. Alright, let's open this up. This is the location of the poles in the complex plane. Here's our S1 and 5, S2 and 4, and S3 here on the real axis. These are on the left half plane. We don't need that. But what's something else that's interesting is we talked about those lowercase t transfer functions. If we plot those out, all three of them individually, we see how they can contribute to the form of the filter. So let's run this one here, see what we get. Open up a little here. By golly, get a hold of it there. All right, numbering from left to right, T1, T2, and T3. All these multiplied together, these three functions, give a low pass formation here. At a normalized rate and frequency at 1, we see it begin to drop off. Our magnitude is not normalized here, it should be at 1.0 if it were. But this shows the low pass structure. Okay, since we have, here are the values of the resistors we're going to use. Resistors we'll use in the circuit. Move these over out of the way. These are numbered backwards from right to left. So let's do a circuit simulation. This is QUCS, Quite Universal Circuit Simulator. So, right over here, and let me get my values for my resistances ready to go. Okay, this is the third biquad on the right here. And so this one, first one is going to be 9.56 kilo ohms and 26.18. Here's my cursor. 26.18 here, and I forgot to hit enter. 9.56 kilo ohms. R4 is 15.06. 06. And R sub A we already know is 10 kilo ohms. RB here is 17.42. And enter. Moving on over to our next second order section here. This is biquad 2, 13.65. 13.65 kilo ohms. And R2 is 27.79. This one is 26.86. RB on the second order section, 10.35 kilo ohms. Double check here, make sure we got all those. For our first order section, the integrator, we only have one resistance calculated. 22.89 kilo ohms. .89 kilos. Alright, let me look at the circuit schematic here. A brief overview, make sure we've got everything entered here. Alright, using 8825 operational amplifiers in the Salon key biquads and in the simple inverter. Alright, let's run this and see what we get. Sometimes QUCS says DC analysis 1 failed. With the Cartesian coordinates, function T, apply. Okay, well, it looks like we've got something that looks like has a There's a low pass effect here up to about 155 hertz. 0 to 155 is our low pass band, and at about 220 some odd we're down near minus 20 decibels at our stop band. So it looks like it works. What I'm going to do now is I'm going to go to an image of this low pass profile that is more clear form. Like that. Here we go. Alright, 5th order Chebyshev low pass filter, 2 sound key biquads, running grade op amp ID 825. Low pass, F pass band is 159 hertz, stop band edge starts at 223 hertz. We're already down at minus 19 decibels at 221 hertz, so we have satisfied our stop band requirement here of at least minus 18 decibels. But here at the passband edge, at our passband frequency 159 hertz, we're down minus 0.28 decibels. We're only supposed to be down minus 0.25. That's probably a problem of not getting exactly the correct magnitudes we need for the exact profile specified. We can change that a little bit. We can massage our design a little bit and we can get it closer, but this is pretty good. Well, there you have it, a low pass 5th order Chebyshev filter based on the equal ripple profile. We showed the method of calculation with Matlab to find circuit elements. Then we ran a simulation in QUCS confirming the low pass frequency response. Our next video may be a band pass filter. And thank you very much.